Okay, so now we are going to kind of combine a couple things. We're going to take some math and combine it to our heating curve. So on page 21, this is what your graph should look like. Again, I apologize. So if you don't want to stand on your head and look in a mirror, then I would jot down it's just the heating curve. So let's remember here you have a solid only, but look at what's happening. It's changing temperature from here to here. So you would use MC delta T, that's because it's a single phase, but that is for the solid. Phase change from this part to this part, that's where we're going to use the math for a phase change. Then here you're heating liquid only, temperature changes. When temperature changes, you're going to use MC delta T. Phase change, you're going to use the energy for a phase change calculation. And then at the end, again, whenever the slope is changing, that means temperature is changing, that's when you're going to use MC delta T. So really it's just doing the same math, but we're just going to put it together in steps. On these pictures, you need to kind of draw a picture to see what is happening. So we're going to start, and I'll be honest, it's with the most annoying. Not hardest, just a little bit annoying. So a couple things I need to know. It's ice, so that means it's water. So we're just focusing right here on the water. And I'm going to draw myself a picture, meaning I'm starting at -40, and I'm going to go all the way up to 130. So the reason is I have to know, does it go through a phase change? Well, for water, I know at 0 is a phase change and at 100 is a phase change. So I'm going to have to heat it. Once it hits 0, it's going to melt. Then once it's all liquid, it's going to heat. Once it hits 100, it's going to boil. And then once it's all a gas, it's going to heat to 130. So when I'm looking at this, every time I see a change in slope, that means it's going to be a different formula. So I have 1, 2, 3, 4, and this one disappeared, 5 different formulas. This is as long as it gets. So we might as well just start with it, the most annoying, and then they can get shorter. So narrow your focus, only look at one part at a time. So for the very beginning, I'm just looking from when it's going from -40 to 0. Temperature changes, so at part 1, I'm going to use MC delta T to calculate. So then I'm just going to plug in numbers. 180.2 is the mass. That will not change. Here's where we have to be careful. It's a liquid. So look at all my C's. I have different C's depending on what state it is in. So I would use a specific heat for a solid, so 2.10. And then how much did that temperature, so I'm looking just at that part of the graph, that changed 40 degrees. Okay, I'm not picking up my calculator yet. Let's get all the math on paper and then we can pick up the calculator. So now I'm going to look at part 2. What am I doing? It's a phase change, so that's going to be grams, heat, and now I have to say which phase change. It's melting, that's your heat of fusion, so it would be 180.2 grams. Heat of fusion is 334, and again, remember this is joules for every gram. So that just took me to here. That would be parts 1 and part 2. So now we're here at part 3. Look at what's happening. The temperature is changing. Temperature changes. You use MC delta T. Mass never changes. This time it's a liquid. You're heating the liquid. So you need the specific heat for the liquid, which is, sorry about that, 4.184. And how much did the temperature change? It went from 0 to 100. That's 100 degrees. Now, part 4, straight line again. That's a phase change. This time the phase change is vaporization. So it's 180.2. And heat of vaporization is 2264 kilojoules, joules per gram. And then we have this last little bit where it's a steam, it's gas only. So how much energy to heat that steam? Well, mass, this time specific heat for a solid. And the temperature change there was 30 degrees from 100 up to 130. Now I'm going to take the calculator, and the order of operations will take care of all of this. So if you just said you don't use parentheses, you just have to say this 180.2 times 2.10 times 40 plus 180.2 times 334 plus. So just do each one, order of operations. And joules are really tiny, and look at, I want it in a kilojoule. So remember, there's 1,000 joules in 1 kilojoule. So you're going to take this answer, whatever you get as your answer, and then divide it by 1,000 to put it into kilojoules. So if you do all that, you should have gotten, it was like 569.5, so we'll round it up to 570 kilojoules. That's how much energy to take that 180.2 grams all the way from negative 40 degrees all the way up to 130. And I can't just do it at 1 mc delta T because we have phase changes we have to worry about. And you have different states. Okay, so let's just try another one. And I promise that's the worst. Because let's look at this one. Again, we're going to draw a picture. So this time it's water. So I'm going to start at negative 10. But this time I want it to go to water liquid. So I want all the way to liquid at 0. So that means I'm going to heat it, and then once it hits 0, it's going to start melting until I get all the way to there. So if you look, I only have 1, 2 this time. Not nearly as obnoxious. So I'm going to have mc delta T when it's a solid, and I'll add that to the heat of fusion to melt that entire amount of ice. So 100 kilograms, so we need to change them to grams. So there's 1,000 grams in a kilograms. This number is going to get big again, so we're going to take our answer and put it back into kilojoules. But 100 times 1,000 is 100,000 grams. Specific heat, it's a solid. So looking on your chart, the specific heat for solid water is 2.10 times 10, because it only heated up 10 degrees. And then the same 100,000. This time we need to melt it, and that's 334 joules per gram. Those are the only 2 steps, so that's the only 2 parts of the math you have to do. And then again, take this answer, divide it by 1,000 to put it into a kilojoule. And it's still going to be a large number because 100 kilograms of ice is a lot of ice. So you should have gotten 35,500 kilojoules. Okay, so I want you to do this last one, but I'm going to help you draw the picture, and there's a few things to worry about. First, it's ethyl alcohol. Ethyl alcohol is the C2H5OH. It's what's on your packet. Now we need to look, so ethyl alcohol, we have different temperatures. Well, we're starting at 70, and we're going to cool it to negative 140. So I need to know, do I go through any phase change? So look at the chart, and it says ethyl alcohol boils at 80 degrees. So 80 degrees is above where I'm starting, so that means I don't have to worry about that one. But then look, it's going to melt at 120. Okay, we're cooling, so we're actually not worrying about it melting at 120. We're going to freeze it. So we're going to kind of think of this backwards a little bit. So this means this is all going to be exothermic because you're going to cool it. So start at 70, cool, cool, cool. Once it reaches negative 120, then you're going to freeze it. Once it's frozen solid, then you're going to cool down the solid to 140. So there's going to be 1, 2, 3 different parts. So you're going to do MC delta T, heat of fusion, because it's freezing, fusion, and then MC delta T, but you have liquid and solid. Now, a couple things. All these temperature changes are going to be negative. Heat of fusion is negative. So each section is a negative Q. So two ways you can do that. Just make sure you either have a negative temperature and then a negative heat of fusion and then negative temperature, or just treat everything positive and throw a negative at the end because you know it's all exothermic. But I can never have something positive, something negative when I'm doing these. It's either all heating up, endothermic, or all cooling down, exothermic. So when you get this answer, you should get negative 64.2 kilojoules. Another thing to be careful, look at this temperature change. Look at this temperature change. You're going from a negative 120 minus 70. So that's not 50 degrees. You look at that, that's 190 degrees. You're cooling it down 190 degrees. So just be careful and make sure you're taking the numbers that you need from that last column for the ethanol. Okay, so then you're finishing this problem, and then you are doing on page 20 just some of the questions about the heating curve, and then there's your last podcast for the year is on page 22 and is about an 8.5-minute podcast. So next time I see you, you should have through page 22 in your packet completed. I will see you next time.